So I want to tell you my ideas which I used for this competition, because I hope that they can be used for someone in the future. So for first, I try to solve this problem by modeling the agent actions into the search space. So instead of creating one node for every cell in the map, I created four nodes, which represent the orientation of the agent, and so in this case, all the actions can be represented by edges in the nodes. And I use the A-star search to find paths for the agents, and I used prioritized planning with a reservation table to merge these plans together, and this resulted in bad performance because the search was slow and the prioritized planning failed in most of the instances. So to overcome these problems, I created a minimal solver which worked by creating independent single agent paths for every agent. And to speed up the search, I changed the representation to a graph where every cell is a node, but the costs of the edges between the nodes are dynamically set to represent the number of actions the location change requires. So in this example, you can see that if I have an agent in the middle, to travel to the east, we can use one forward action, so the cost is 1, but to move in the north, we have to use a rotation and then a movement action, so the cost is 2. And with this model of the problem, I get faster search. And to resolve the conflicts, I used a very simple conflict resolution algorithm in which I checked the possible conflicts between the agents and stopped the agent who would cause a conflict. So if an agent want to turn in his location and another agent want to step on that location, the one who want to step on that location will be stopped, and his action is changed to waiting. And I search for cycles and following cases and try to allow most of the movement and only stop agents if I must. Another idea which I used is to create limitations for the map, as the others also tried this, but I was very strict and I removed edges from the graph. So I have a smaller search space, but fewer options for paths. And this resulted in faster search, but the found paths were sometimes longer than in the other cases. And I created the limitations by this crisscross pattern. And to speed up the search, I noticed that the single agent path findings are separate tasks, so I can use a thread pool to compute them parallelly. And then I realized that I'm only using the first step of every path, and I should not calculate in every time step for all the agents. So I started caching the computed paths and only use the already calculated paths and only calculate a new path for the agent who reached their task location. And another idea I try to implement and use is I have this situation, as you can see in the example, that agents are waiting in the lines because, like in this random map, the shortest paths for them were very similar. So they started waiting in these lines, and I get an idea from real world traffic where the drivers who are waiting in long lines are get frustrated and seek for alternative paths to travel. And I implemented this idea as I count the waiting time for the agents, and if it reaches a limit, they step in every available direction next to them and calculate a new path, which is hopefully better than the previous one. And these ideas were slowly improving my results, and in the uh, last attempt I reached the 5th place in the competition. And I thank for your attention, and sorry for my technical problems.
Okay, Augo, thank you for the talk. And we have questions from the audience. Okay, so I'll do.
Hello, thank you for your presentation, Márton. And I think I lost something. I don't understand. How could you compute paths in parallel with multi-threading? I guess you have problems with agents that go in the pass by the same point. How do you do that?
The way I can do that is because all the path plannings are independent from each other. They only require the map as the input and the starting and the finish position. And if when I plan for an agent, I didn't count any other agent's movement or anything. So these are independent problems.
And if you have a corridor, let's say of 1 pixel thickness, and you have an agent that wants to go in one direction, another agent that wants to go here, what will happen with your algorithm?
In the conflict resolution, they will be stabbed to prevent a collision, and that is not the best thing. So I tried the limitations to resolve this corridor problem, and these rule-based limitations are not the best for solving that. So I also tried to create limitations by hand in the last few attempts in the competition, which sometimes solved the narrow corridor problem.
Okay, I understand now. Yes, thank you. Thank you very much.
Thank you for the question.
We take one more question from Zhang.
Okay, thank you for the talk. I also have a question about parallelism. It's like how you cache and reuse the paths in the competition.
So I stored all the calculated paths as a list of locations, and that is what I stored. And in the beginning of a planning phase, I checked if an agent reached its next location in its stored path, and if he reached the first location, then I remove that from the list, and the agent got a new action based on the next location in this list.
So do you reuse the path, or after the agent follows the path and then you remove the path from the cache?
No, I reused all the paths. Just remove the first step, which it already took.
Okay, I see. Yeah, thank you.
Thank you for the question.